Alright, we're going to talk 4.2 today, and we're going to talk about the second derivative test, which lets us know about the concavity of the graph. So we're going to talk about inflection points, intervals of concavity, and sad to say, but we're going to make the list longer. Up until now, we've been talking about increasing, decreasing, local maxes and mins, absolute maxes and mins, and we're going to take it a little bit further today as we build the graph. So first, a little recap on where we left off. Recap from 4.1. We talked about when the slope was positive here, f prime greater than 0, it meant it was increasing. We know that we have local maxes and mins when the first derivative is 0. And we know that when the slope is negative, this graph is decreasing, f of x, the original. So we have increasing, positive, decreasing, negative, mins and maxes, locals, derivative 0. We also talked about when the derivative was undefined. Those are also possible maxes and mins. And we'll talk more about that and look at more scenarios as the week goes on, this upcoming week. And we also talked about don't forget to test your endpoints, if we have endpoints, because those can also be absolutes. So we definitely need to test those as well. So moving on to today, we talk a little bit about how the slope changes. This goes back to the acceleration, position, velocity, acceleration talk that we had a while ago, back when we talked about more physics kind of stuff. But one thing I want you to notice here is that as the slope gets flatter, this is called concave down. As the velocity or the slope gets less, it's going to curve your graph this way, and that's called a concave down. Now as the thing gets steeper, as it gets steeper this way, that's called concave up. So we've got flat, steep, and it depends on which way it opens. The way the graph opens is determined by concave up or down. And this is also determined by how the slope is changing. Slope increasing, it's going to be concave up. Slope decreasing, concave down. And they got the little note here as how y prime changes determines how the graph is curved. So that brings us to this thing called the second derivative test. If we have a twice differentiable function, y equals f of x, we know that it's going to be concave down. It's going to open downward. If the second derivative is less than 0, because that's going to tell you that the slope is changing. It's getting less steep. It's getting less steep, which is going to make it concave down. And vice versa, concave up means it's getting more steep. As the velocity gets steeper, that means the second derivative, or the change in the velocity, is positive. So these two pieces alone let us know when a graph is concave up and concave down. And the one thing that we also need to throw in there is the point where it's changing from concave up to concave down is called a point of inflection. That's the one point where it's changing from one to the other. And at a point of inflection, that's where your second derivative is equal to 0. That's where it's going from positive to negative, or vice versa, and it's where it's hitting 0 right on the money. Or I should throw in there undefined. And we'll talk about that as well some more this week. But let's take a look at an example. So here we're going to put together a list, and we're going to graph this thing. I think what I want to do first is real quick just pull out the graph. So it looks something like this. So here's what I'm thinking is going to happen. It looks like my graph is increasing. It looks possibly like it might be decreasing and then increasing. It's a little hard to tell what's going on here. My scale's really not going by 1, so it's hard to tell. It definitely looks like I got some concave down to concave up. And I guess that's some things I'm expecting to see. Let's drag this over here, get it out of the way, and let's see what the calculus tells us. So the first thing I'm going to do is y prime. So I'm going to take my derivative. This tells me increasing, decreasing, and it also tells me local maxes, local mins. So first thing we do is we take our first derivative, we set it equal to 0, and we solve for x. This gives us critical points, and it also, we need to think about where it's undefined. Now this is a nice polynomial. It's never undefined, so we just need to find the zeros. So let's factor this thing. I think it factors nice. -1, -1. Double check me, but that looks good to me. Looks like I have a couple of critical points. I have a critical point at 1/3, and I have a critical point at 1. Number line. We're going to test it. This is the first derivative test. I'm going to test 1, 1/3. I want the intervals in between. So if I test a number like, now we're plugging this into the derivative. So if I plug in a number like, oh, say 10, something over here to the right, if I plug in a 10 here, I'm going to get a huge positive, and then I'll subtract some, but I know it's going to end up being positive, which means increasing. I'll plug in a number like, well, let me go over here first. Let me plug in 0. If I plug in 0, 0 minus 0 plus 1, positive, which is also increasing. And now we got to plug in a number here. Oh, let's say like 1/2. If I plug in 1/2, this one might take a little thinking. 1/2 squared is 1/4, times 3 is 3/4. If I plug in a 1/2 here, I get 1/2 and 4 is 2. So I get -2 plus 1. -2 plus 1 is -1. 3/4 minus 1 is negative. So I am decreasing in that region. So that means that this is a local positive going up to negative, down. That means I have a local max. And that means this is decreasing to increasing. That means this point is a local min. All right, I'll put the list here together in a minute, but this tells me about my maxes, mins, increasing, decreasing. Now the new idea today is, let me slide down a little here. We're going to go, and now we're going to add to the list concavity. So I'm going to take my second derivative. And my second derivative looks like 6x minus 4. Is this ever undefined? No. But it is equal to 0. And it is equal to 0 when x equals 4/6, which is 2/3. New number line. New number line, throw the 2/3 on there, test your intervals. Now we're not plugging back into the derivative. I don't care about the slope here, I care about the concavity. And that's what the second derivative tells us. So I'm going to plug in a number like 1. If I plug in 1, I get 6 minus 4, which is 2, which is positive, which means concave up. CU, concave up. I know my graph is going to be curling up. Now I'm going to test a point over here to the left. Oh, let's say 0. I plug in 0, I get negative. That means concave down. I think this is all tying in nicely with this graph that we took a peek at. Let me tap off. Concave down, looking good, up to 2/3. 2/3 is probably hanging right about there. At 2/3, this would be called an inflection point because it's changing concavity, negative to positive. And then if we talk about increasing to decreasing, it's increasing to 1/3. It's decreasing to 1. So there's just a tiny little piece there where it's decreasing. And then it's back to increasing. Okay, local max, somewhere in here. Peaks, goes down, goes back up. The scale makes it hard to see here, but the calculus is showing us exactly what's going on. So let's build the list. Okay, I'm going to see what we can do here. So I know that I am increasing, decreasing. I know that I have a local max. I know that I have a local min. I'll list them out here in a sec. I know that I'm concave up. I know that I'm concave down. And I know that I have an inflection point. So let me scroll back up here. Looks like I'm increasing at 2 points. Now this does not have a limited domain. It's everything, all real numbers. So I have to list everything. Negative infinity to 1/3 and 1 to infinity. Negative infinity to 1/3 and 1 to infinity. And it was decreasing between 1/3 and 1. I had a local max at 1/3 and a local min at 1. I'll leave the y values here for a minute. I know that I'm concave up in this region right here, which is 2/3. Remember, these are interval. This is interval notation. And I know I'm concave down to the left here. Negative infinity to 2/3. And I know that I have an inflection point at 2/3. So I guess the only thing I'm left to do here is to go back, plug in 1/3, plug in 1, plug in 2/3, plug those back into, not the second, not the first, plug those back into the original. And when you plug those into the original, they will kick out a y value, and that is an actual point on the graph. So I'm going to go and plug those in, and I'll hang out one sec. All right, I'm back. I grabbed out my handy dandy old school TI-82. Yes, still have one of these. The battery's dying, so I'm going to see. At 1/3, it looks like I have a, actually I have my pen here, 29.85 negative. 29.85. Ran out of room, sorry. At 1, I have negative 30. And my inflection point is at negative 29.93. As you can see, there is not a whole lot of room for error here. There's a tiny little dip here. We have a local max. I'm going to go back to my graph here. Let's see what I can show here. So my local max is at 1/3, which is like right about here. Negative 29, which is here. I have a local min, which is at 1, which dips down to negative 30. There's a tiny little dip down here. And then an inflection point at 2/3, which is right about here. That's where I'm changing from the concave down, boom, to the concave up. So visually, you can't see it. Calculus shows us exactly what's happening there. Monday in class, we are going to practice a lot of this. I'm going to have you work in groups and do some graphing, and some with calculator and some without. And we'll see what we can do. As the week goes on, we'll start to look at a little more complicated things. Polynomials they're not easy, but they're the easiest of the bunch. We start looking at some rational functions, and it gets a little bit messier, but we'll get there step by step. So please, I hope you watch this, and I hope you bring questions on Monday, and we will definitely dive right into practicing making this list and putting some graphs together with groups. All right, see ya. Bye.